Uh, Good day everyone, I'm Professor. So for this project I would like to present my work, direct conversion of furfural to 1,5-pentanediol over a nickel cobalt oxide alumina trimetallic catalyst. So this is my current work that already published in Applied Catalysis journal. So actually in here I would like to focus on converting the biomass to value-added chemical using catalyst. So in here I use furfural or FFA. It's one of the key renewable intermediate produced by the acid catalyzed transformation of C5 sugar in lignocellulose biomass can be hydrogenated to obtain a variety of high value products such as the partial hydrogenation of furfural to furfuryl alcohol, and then for the ring opening to produce 1,5-PDO or 1,5-pentanediol, and also 1,2-PDO or 1,2-pentanediol. In here, we would like to focus on 1,5-pentanediol because it's one of the most expensive value-added chemical, and with a global market value around 28 million USD in 2020 that is expected to reach more than 42 million by the end of the 2027. So in here there are several previous work that already been done by several researchers around the world. So the first figure, it was researched there are two-step reaction for the furfural partial hydrogen total hydrogenation to THFOL, and then the further hydrogenation ring opening to 1,5-pentanediol using the noble metal catalyst. And then another one in the right side, there is also multi-step hydrogenation of furfural to THFOL, and then there is like a dehydration and hydration and ring opening to produce 1,5-pentanediol. In my work, I would like to focus directly convert furfural with the intermediate furfuryl alcohol to directly 1,5-pentanediol using one-pot conversion with the trimetallic catalyst that I designed. So this is the catalyst preparation method. So actually I use nickel, cobalt, and alumina mixed three metal using co-precipitation method, using the sodium carbonate, sodium hydroxide as the co-precipitant, and then aged for the overnight, and then dried and calcined in the hydrogen environment. And also there is two-step hydrogenation, like first burn in the air and also burn that, and the second step is the reduction. So we give the name as it is in here: NCA, N is nickel, C is cobalt, and A is alumina with the specific ratio. And then I also synthesize the co-precipitation metal like bimetallic, like nickel alumina, also bimetallic cobalt alumina, and nickel cobalt as the reference. And then for the catalyst characterization, so actually the first figure is the figure A, which is the XRD, and it's showing that almost all the catalysts like trimetallic catalyst, nickel, cobalt, alumina, dominantly showing only nickel oxide with the harm, and also there is no alumina peak, and also there is no cobalt oxide peak. So we can see that it might be because of the amorphosity of the character amorphosity of the catalyst. And then in the B figure we can clearly see the XPS images from the nickel and also from the cobalt, and also we can clearly see the alumina. So we can see that we have alumina in the surface, we have cobalt in the surface, but we cannot observe it on the XRD because the small particle and also amorphosity character. And then we also characterize the XSAF analysis, and based on this XSAF profile we can see that the nickel is dominantly in the oxide phase, and also cobalt also dominantly in the cobalt 304 phase, with a lot of the oxygen vacant side that we will discuss more in the back. So actually we also check the TEM result, specifically using STM images. So we clearly see that we have a nickel oxide plane, cobalt 304 plane in the catalyst, which is side by side, like they have neighboring for each other, and then it has a very small particle size around 5 until 10 nanometer for all the three catalysts like nickel, cobalt, alumina, for each 3 catalysts. And then to check the reduction pattern, we did H2TPR, hydrogen temperature program reduction, and also oxygen TPD to observe the oxygen vacant site. And we can see that the catalyst, which is nickel cobalt alumina, we directly reduce process without any oxidation treatment. We clearly see that we have a lot of oxygen vacant site in the cobalt surface, because we already test the reference, and we can clearly see that the catalyst, they have it has a lot of oxygen vacant site. And also in hydrogen TPD case, we want to know if there is any hydrogen desorption and also spillover in the catalyst, and we can clearly see that in the monometallic bimetallic nickel alumina, we have surface desorption and also spillover with high temperature. And also in the cobalt alumina, it's only high temperature desorption, which means because of the spillover. And then in case of nickel and cobalt, we only have low temperature, which because of the directly desorbed hydrogen from the surface. And then in case of trimetallic catalyst, it have like spillover and also it have surface desorption. So actually we also characterize the catalyst for the acidity using pyridine FTIR and ammonia TBD, and also CO FTIR to check this how the electronic environment and the metallic surface of the catalyst. So actually we confirm that in fact, based on the pyridine FTIR, we only have the Lewis acid site, and based on the ammonia TPD, we dominantly have only the weak and medium strength acid site. We don't have very strong acid site. And then based on the CO chemistry also, based on the CO FTIR also, actually we have edge step and also the terrace kind of the surface of in the nickel metal side with a very small domain. And then we also discuss catalyst characterization, actually based on this the temperature effect and pressure effect and also time effect. We can clearly see that the with the higher temperature we can get the more 1,5-pentadiol directly from furfural, and also with higher pressure also we could get more product that we desire. So actually based on this overall result, we got more than 47.5% yield for the 1,5-pentadiol directly from furfural. Also we did the catalyst recyclability. Actually based on the catalyst recyclability, actually the for each run, from the first run to second run and the third run, fourth run, the catalyst keep dropping. It might be because, and then why it's happening, we check the oxygen TPD and also ammonia TPD, and also we check the TGA. So actually based on this profile and characterization, we confirm that it lost the oxygen vacant site because of the oxidation during the catalyst. And also there are the acidity changes, and also some nickel reduction, more nickel oxidation. So because of the oxidation nickel and also the oxidation of cobalt 304, oxygen vacant site to be a perfect oxygen vacant site. So we need to reactivate using the burning, because we also find small of the small amount of carbon deposit that block the surface active site based on the TGA. So we need to burn in the air and then reduce again hydrogen environment in the calcination tube to make the nickel reduced state and also oxygen vacant site on the cobalt 304, so it can act together as the catalyst surface and as the active site in the catalyst surface. And then after we reactivate, we can regain the activity. And then we can conclude that the trimetallic nickel cobalt alumina is efficient for one pot conversion of 5A to 1,5-pentanediol with 47% yield, and then low exposure ultra small nickel domain less than 5% is enough to activate the reaction. This result is based on the detailed discussion of XSAF that we can clearly confirm. If you want to read more, you can read the paper with similar title that I already published. And then from the DFT simulation, actually I did DFT simulation to confirm the electron enriched cobalt oxide is the active for the furfural and furfural alcohol absorption, and also recyclability tests show that the oxidation nickel and oxygen uptake of oxygen vacant site is the main deactivation